All right, Dr. Matthew J. Traum here. This is a video where I'm going to talk about 2 ways to distribute tolerance. And this video is meant to follow on an example that I just did that shows how to figure out the tolerances to make sure that an M2.5 bolt, M2.5 by 0.4 bolt, will fit inside the hole of any M2.5 by 0.4 nut. So I'm going to use some of the numbers from that example, but I wanted to make this its own standalone video, just in case you wanted to kind of see this technique or see this this material separate from the example. So I'm going to use those numbers. That's where they came from, but this video is meant to be kind of standalone on its own. So there's 2 ways to distribute tolerance across parts. The first way, which we talked about in the example that I just did, is called equal distribution. And the second technique is called equal precision. Okay. And equal distribution is basically described as all the tolerances across parts are the same. And for equal precision, it's all tolerances across parts are scaled by their nominal dimension. In other words, all dimensional precisions, all dimensional precisions are identical. Okay, so we already kind of talked about how this worked in the example that I just gave, but we're going to start out with equal distribution, and I'll just give you kind of the math underpinning it. So equal distribution, okay, and the underpinning math is just the idea that any tolerance in an equal distribution tolerance loop is equal to the sum of all of the tolerances in your loop divided by the number of nominal dimensions. Yeah, there we go. Okay, that's a better notation. Instead of just n, we'll call it, I got blurry here. There we go. So it's the tolerances are equal to the sum of all available tolerance in that loop divided by the number of nominal dimensions that you have. So that's what that's meant to represent. So in our last example, we had 3 different nominal dimensions. So n nominal dimensions, that was 3. And then remember the sum of the available tolerance that we had to us when we calculated it out from the tolerance loop was 0.110 millimeters. And so in that last example, each one of those tolerances would get an equal share of that 0.110 millimeters, like so. And when we did that, it worked out to be 0.0367 millimeters. So you would use this in situations where all the features are about the same size. So when when all part features are similar in size. Because if they're all similar in size and they all have similar or identical tolerances, then it's equally difficult or equally easy to make all those pieces, and you've basically distributed the difficulty equally over all of them, hopefully minimizing the difficulty along the way. So the drawback of this approach is if you have smaller features. So if an assembly has some very small features, you could end up in a situation where the tolerances become a high percentage of nominal dimensions. So tolerances become a high percentage of nominal dimensions. And you can even run into a situation in extreme cases where the tolerance is actually bigger than the nominal dimension, right? So you could end up specifying a dimension where, you know, maybe this is like 1.00 plus or minus 1.50 or something like that, right? If you allow the tolerance to get too big because you've done this equal distribution process. One part is really small, the rest are really big, so you end up with a big tolerance that ends up then kind of gobbling up the nominal dimension. So you want to kind of check for that, and if parts are different sizes, usually an order of magnitude bigger, an order of magnitude smaller in your tolerance stack up, then you probably don't want to use this. But for situations where everything is the same size, equal distribution is mathematically very, very simple to do, right? It's just one step. So the other approach is called equal precision. Equal precision. And the idea behind equal precision is that instead of making the tolerances equal, you want to make the precisions equal. So want to make the precisions for each part feature equal. Okay, and you would use this when features of an assembly differ in size at least by an order of magnitude. So use when feature dimensions on an assembly differ by at least an order of magnitude. So you've got big parts and you've got small parts, and they're together in a tolerance stack up. And that's when you would use this situation. So you don't run into something like this where the tolerance ends up being bigger than the nominal dimension of the small parts. So the way that we do this mathematically is we already have the expression for precision, right? Remember that precision is just the tolerance in the dimension divided by the dimension. And so we want to just set our precisions for each of our whoops, that's 2, that's 3. Our precisions for each of our dimensions to be equal to one another. And so I'm going to just say here that the uncertainty in R1 over R1 is going to be equal to the uncertainty in R2 over R2 and equal to the uncertainty in R3 over R3. There's a little bit of kind of mathematical complexity here. I won't show you how to do this derivation. It takes a little while, but it turns out that there's a technique in partial fractions, so we're going to use a partial fraction identity. And if you've got a series of kind of ratios that are equal to each other, it turns out that the sum of the numerators of those ratios is equal to the sum of the denominators of those ratios. And again, I won't derive this for you. You can find this identity, but that's how it works out. And so then, in general, then, if we're applying the equal precision technique as opposed to the equal distribution technique, it's the sum of the tolerances is equal to the sum of the magnitudes of the nominal dimensions. So what that translates into is basically delta R1 over R1. And remember, this is just the precision, so if I were to actually calculate this out, I would say that delta R1 is equal to the precision associated with R1 and then times R1. And that's how I would get my result. That's how I would set my tolerance. So instead of like before with equal distribution, I could just solve all three of those tolerances in my particular problem all at once. This is a bit more mathematically complex because you have to then go back once you calculated the precision and solve for each individual tolerance, so it's a little more time consuming. But if you run into a situation where your tolerance is as big as your nominal dimension, that's bad. And so you want to use the equal precision technique if you've got a mixture of parts with large and small nominal dimensions that are in the same tolerance stack up. Okay, so that's all I want to say about equal distribution and equal precision. Thanks for your attention, and I'll see you in class.